Okay, so how is everyone today? Good? All right. So as a reminder, 2 days from now, we're going to have quiz number 26, I think is the number. Exercises will be, it will consist entirely of redo exercises. The coverage is up to and including 16. And good. Any questions about that? Then tomorrow, of course, is Pi Day. That's good too. All right. So, sort of covering a little bit of what we said last time. So here's a nice reminder of handedness, the handedness convention. Is that in R1, the convention on the page is that when you're drawing an R1, it'll be a horizontal line, and if you want to talk about a left-handed horizontal line, then it needs to be pointing to the left. And if you want to talk about a right-handed horizontal line, it needs to be pointing to the right. And then, you can kind of understand that by remembering that the convention is that on the page, you're looking at it, in the normal way. Like the page is right here in front of you and you're like this. So, there's like an eyeball, like right here, you're looking at it like this, blah. And, from your point of view, it's going to the left. And similarly, this one, from this point of view, it's going to the right. And then in R2, R2 is just like R1, except now it's got two axes, and they're at right angles to each other. So, so we have this and this. So that'll be those are at right angles, and then we've got this one and this one. Whoops, I don't want to draw that yet. And so these are at right angles to each other, and this is the left and right. And then, the standard convention when drawing it on the page is that, we're looking at the page in the normal point of view. You got the page in front of you, just like it normally looks. Then sort of the standard way that we do this is that in both the left-handed case and the right-handed case, we're going to make the horizontal axis going to the right. And this one is going to be the first axis. And then the way it's going to end up being most of the time is that there's going to be two variables, and very often they're going to be called x and y, and so we'll refer to this one as the x-axis and that one the y-axis. But for now, just first axis and second axis. So what we want is this one to be the left-handed result and this one to be the right-handed result, which means that concerning the second axis, one of them needs to be going down and the other one needs to be going up, and it needs to be in agreement with the handedness convention. So the handedness convention on the page is that for this, the handedness is indicated by the barbs only, going to the left or going to the right. But for two-dimensional handedness, that's indicated by a swirl, and the way that you do it is you take whichever handedness you want. So I'll do left-handed first. You take your left hand and you hold your thumb up out of the page, coming up out of the page, and then curl your fingers. So from your thumb to your fingertips, do you see that that's going clockwise? So left-handed swirl is clockwise, from thumb to fingertip. Whereas right-handed orientation is now take your right hand and your thumb and hold it up out of the page, and then curl your fingers to your thumb. So from thumb to fingertips, that's counterclockwise. So that's right-handed. And, you know, you can just remember that the right-handed convention is that what should be the case with the vertical axis? It should be going how? Down or up? Yeah? You have a question? Or are you saying up?
No, up.
Okay, good. So it's up, like that. And then, you know, by process of elimination, this one is down. Now, the reason for this is that you can imagine, you know, the page, you're like, you can imagine it like you're looking down at a cup of coffee or whatever kind of thing that you might imagine to be stirring. So you put your, you know, you put your spoon in there, you know, so put it wherever point that you like. And then the stirring, the way that stirring occurs is you follow the first axis a little bit. So that means go to the right. And then you follow the second axis for a little bit. So in this case, you go up. And then because we're stirring, you know, we need to make a loop. So that means that we're going to be going like this. So right, up, and then loop back. So notice that that's right-handed. Okay, similarly, over here, choose any point that you like. For example, say this point. And if you follow the first axis a little bit, now we need to make a right angle turn. So which way are we going to go now? Down. And fine. So then that means that the stirring is going to be like this. So notice that that's left-handed, clockwise. Okay, so now here's the question. So add the barbs to produce the indicated handedness. Okay, so then, so here's one situation. Oops, no barbs yet. And I'll say that we want this to be left-handed. And this is R1. And this is the point of view, like this. And for this one, we want this to be, so this is R1, and this one will be R2. And we want this to be right-handed. And, you know, maybe like this. Like this. And we'll say that this one is given. And that this is the say first axis, and maybe we have another one that this is R2, and we want this to be left-handed, and maybe it looks like this. So of course these are at right angles to each other. And maybe what's given is, say, this one, I guess. And maybe this is the second axis. Okay. So in some sense, what I'm requesting is that, you know, for you to draw the barbs. That's what I want. So, you know, you've got to fill in that bit, that bit, that bit, that bit, that bit, and that bit. So you've got to put the correct barbs in each one of those situations. So this is R1, and we want left-handed. Okay, so how do we do it? How do we make it left-handed? What do you think? Well, the idea is that remember that the convention on the page is that under normal circumstances, ignoring weird circumstances like this, we're going to draw the R1 as a horizontal line, and from our point of view, when it's pointing to the left, that's a left-handed one, and when it's pointing to the right, that's a right-handed one. So I drew some weird old slanted line there, and I want you to make it be left-handed. And the only way to make that question make sense is for me to also indicate the orientation from which you're observing it. So I indicated that for you. So here's the best way, is that notice that we look at it like this. So let's take the question and look at it in the normal way. So, now we're looking at it like we do usually. How do we make it left-handed? Yeah, to that way. Any question about it? Okay, so that's fine. Now, this one, we're looking at it from the top. Now, if I was writing on, I don't know if y'all have ever had the experience. Now we use these document cameras, but there used to be this similar device that fulfilled a similar role called a projector, and you would write on, and the instructor would write on these like clear pages, and sometimes they'd be individual clear pages, but also sometimes they had like a roller. At any rate, but you could see through them. But this isn't clear. But if it was clear, then you could flip this over, and you can just barely see what I drew there. Okay, but that's not legal. We have to look at the page from the top. So we have to be looking at it from the top. That's the only point of view that's allowed. But we can twist it however we like, but we have to be looking at it from the top. So we want this result to be right-handed. Well, there isn't an up. I don't know what you mean. So I take it to mean you want me to put the barb there, the forward barb there. Okay, now how are you seeing that? What makes you say that?
If you turn the page and the barbs are going to the right,
Mm-hmm.
you have the other one perpendicular going up.
Okay, so right, we're accustomed to looking at it like this. It is like the standard way. And so now I made it all, messed up. So to get it right, you say, well, we always arrange matters in the standard configuration so that we've got two axes and the horizontal one is pointing to the right in both cases for left and right-handed. So the first axis is pointing to the right. So there's the first axis, and let's just make it point to the right. So now we're looking at it sort of in the standard point of view, and the requested handedness was right-handed, so this axis needs to be going up from this point of view. Can you see it? Now, even if this is a perfectly legitimate way to go about doing it, but let's double check our work, okay? Because maybe all this twisting is hurting your mind. A lot of people don't like this twisting thing. That's fine. So the right-handed convention is that swirl should agree with your right hand. So it should be counterclockwise. So we want this. So what's desired? That's what's requested. So now let's follow the rules as it's written. So choose a point that you're going to stir. Any point, it doesn't matter. So how about this one? We're going to stir from there. And then the rule is that you follow the first axis first and then the second axis second. So from here, we're going to follow the first axis, which says that we're going to go, that away. So follow the first axis. And then after you follow the first axis a little bit, now follow the second. And we said up, so I'll go up. And now, we're stirring, so we've got to make a loop. Now, is that right-handed? It is. So we did it right. We did it correctly. Any question about it?
How's the right-handed?
Because this is, you can imagine it like this, is you've got thumb right there coming out of the page, and then your fingers do this. Thumb, fingers.
Oh.
Yeah, and then this one is similar. Okay, fine. So how about this one?
Same direction as the last one.
So it should be going up?
Yep.
Okay, like this? Okay, now why?
Since the line that we're given is the second line,
Uh-huh.
since it's going to be a left hand, it's going to be pointing down relative to the page, or relative to our usual alignment of a page to ourselves.
Okay.
And then the first line always will go to the right relative.
Okay. So let's write this down. So what's requested, there's lots of ways to see it, and it just depends on whichever way you like best. Just depends on how you are. So what's requested is left-handed. So this is what's requested. Okay, so we want that. Now here's one way to see it. It sounds like this is what y'all were saying. Now in the standard point of view, the first axis is horizontal and pointing to the right. So what we're looking for is to make this left-handed. So now the second axis is going to be vertical. So let's take the second axis and let's make it vertical. And because we want it to be left-handed, let's make it like that, because this is what left-handed would be. So now we're looking at the second axis and it's pointing down. So then now, what about this one? It should be going to the right, because that's the first axis. Alternatively, you could say, well, if we make the second axis point up, then I know that if the first axis is pointing to the right, that'd be right-handed, so I need it to point to the left, so that it'll be left-handed. Okay, but in either case, however you see it, you can always verify your result as follows. Just choose any point and stir according to the convention that is indicated. So here's a point, and this is the first axis. And the convention is that first you follow the first axis a little, and then the second. So from here, we need to go to the left. And then we'll follow the second axis. So we go up. And then we're stirring, so we need to make a loop. And then the question is that left-handed or is that right-handed? That's left-handed. And that's what was requested. So can you see it? Good. So, this is the, it's even, more fun to draw, a three-dimensional situation and say, complete it so that, that this is a left-handed three-dimensional world or a right-handed three-dimensional world. And then, this handedness continues into any dimension that you want. So, like, there's a, concerning, say, 7-dimensional space, there's a left-handed version and a right-handed version. Okay. Neat. So this kind of thing, figuring this out, that's for those of you who, say, want to be a physician, a doctor. You've got to get that figured out in order to pass organic chemistry. So in that case, you're trying to, one of the big tasks in organic chemistry, that's a geometry-like task, is to look at a carbon atom that has 4 bonds and then figure out, is this a left-handed carbon or a right-handed carbon? And you've got to do basically that same thing that we were just doing, but in 3 dimensions. Okay. And so all the time in such a organic chemistry exam, you'll see students, doing this, trying to get it figured out with their hand. It's funny. All right. So then, fine. So the next thing that we need to do is this. So we'll call this remark logicals. So we already have these sets. We already have the naturals and the integers and the rationals and the reals. So these are sets that we know and love, and then they're written in that sort of fancy looking way where they're kind of like one part of them is boxy, you know. So now we have a new set, and it's called the logicals. It is denoted with fancy L. So fancy L, and it has just two elements in it. They are denoted with F and T, and their meaning is false and true. So, and it, you know, they mean what you know them to mean. So I can make a statement, and the statement, you know, the statement could be false or true. So I could say something like, you know, I'm holding a pencil. Okay, well that's a statement, and it's either false or true, and in this case it's false. I mean true. And I can make another statement. I could say, you know, I'm holding a taco. Well, that's also a statement, and it's either false or true, and in this case it's false. Okay, so that's all that that is. So those values, false and true, the set of all those values is called the logicals. So the place that this comes up the most is in the following way for us. So we're going to have the definition of an equation. Now we have used equations so far, but now we're going to sort of like get really into the fine details of it. So an equation is a statement consisting of two expressions which evaluate to a real number. So and the symbol equal between them. And equations value may be undefined or illogical. Meaning that concerning an equation's value, there's three possibilities: is that it's either undefined, it is false, or it is true. Those are the only possibilities. So now we're about to make a hard departure from what you might what might have already been your experience about equations. So you know, so get get ready for it, I guess, is what I'm gonna say. So first, consider 13 plus 1 is 14. So now, the first question is that is it an equation?
Yes.
Okay. Yes. Why is it an equation? So the answer is yes. But in the end, here's the reason, is that look at the definition. An equation is a statement consisting of two expressions, and those expressions evaluate to a real number, and the symbol equal is between them. So, you know, unless things are going really weird, you know, you write equations like this, and this left-hand expression will be referred to as the left-hand side, and the right-hand expression as the right-hand side. You know, so this is just the typical names. So left-hand side, right-hand side. So is this an equation? And the answer is yes. But understand why the answer is yes. The answer is yes because it has a left-hand expression, it has a right-hand expression, and there is an equal in between them. That's the reason why it's an equation. So, you know, it has a left-hand side, it has a right-hand side, and it has the equal between them. Okay. Now, what's the value of this equation? So what's its value?
True.
It's going to be true. So now let's figure it out. So here I'm just going to copy the equation 13 plus 1 equal 14. And you know, there's a left-hand expression and a right-hand expression, and all of the work that we've done, like doing arithmetic and various symbolic stuff, collecting like terms and all that, we're allowed to do that, but completely in isolation. So we're allowed to work on the left-hand side in isolation. We're allowed to work on the right-hand side in isolation, but for the time being, it's not permitted that we should do anything to both sides. That's not allowed. Now, 13 plus 1, that can be simplified to what? 14, right? No, not a trick question. So 14, and then 14, that's already as simple as it gets. 14. And so now, this, you know, its value is either undefined, false, or true. So what's its value? True. So the value is true. Okay, fine. 2. And this is where, so you might have had the sense in here that you're not even sure why I'm saying these things. So here's where it, if it's going to go off the rails for you, it's going to go off the rails right here. Consider this. So 14 minus 1 equal 14. So first question, is it an equation? Yes. Now, if you're feeling uncomfortable about that, then don't worry, you're in good company. But so the answer is yes, it is an equation. Now, why is it an equation? Right. It's got two expressions, a left-hand side and a right-hand side, and an equal in between them. So is it an equation? Yes, it's an equation. Then I could ask, what's its value? It's false. Now here's the reason, but understand the reason is that we can take this equation, 14 subtract 1 equal 14, and then we can simplify both sides so that the result looks like this, so 13 equal 14. And now here's the place where you know, if something's going to go wrong, here it is. So what I'm pointing to, is it an equation?
Yes.
Yes. What's its value?
False.
False. Now that's not like a moral judgment on the equation or something like that. It's an equation. Its value is false. So is that one an equation? Yeah. its value is true. Is that one an equation? Yes. Its value is false. Okay. And then, consider something like this. Consider, say, 10 over, say, I don't know, 9 minus 3 squared equal to 8. All right. So is that an equation? Yes. It's an equation because it has two expressions, a left-hand side and a right-hand side. And even I'll make it, maybe 8 plus 1. I don't know. It doesn't matter. So it has two expressions, a left-hand side, a right-hand side, and an equal in between them. Is it an equation? Yes. Then we could ask about its value. Well, what's its value? It's undefined. Because in the end, if you take that equation, 10 over 9 minus 3 squared equal to 8 plus 1, and simplify in isolation both sides, then the right-hand side, the simplest representation is 9. And then notice that that'd be 9 minus 9. So the left-hand side would read 10 divided by 0. So, in order to have a value, in order for the equation to have a value, both expressions themselves must have a value, and moreover, to have a value, both sides must have a value, and then to be true, those values must be the same, and false otherwise. So that's not defined, and as a result, the value of this equation is undefined. Okay, so now the purpose of me writing down these, really, super simple things, is I need to cleanly separate something for you that normally is not cleanly separated by the time you get here. So very often students get here and they'll look at this and I'll ask them, is it an equation? And they'll say no. Well, it is an equation. And if you are saying, no, it's not an equation, then in the end, the reason why is because I'm saying a question, and you're hearing a different question. So the question I'm asking is this an equation? And if you're saying no, then you think the question I'm asking is this an equation whose value is true? In that case, the answer is no. But is it an equation? Yes, its value is false. It's the situation, if you're having difficulty, the situation you're in to make a physical analogy would be something like this. Suppose you went your whole life and you've seen plenty of pens in your life, but every one of the pens that you've ever seen has been a blue pen. And then I ask, is this a pen? And you say, yes, that's obviously a pen. Why are you asking that question? And then I say, well, how about this? Is this a pen? And then some folks will say, no, that's not a pen. And then, why not? Well, because it's not blue. Well, surprise, surprise, actually there can be pens that are red. We're in the same situation here. Is it an equation? Yes, its value is true. Is it an equation? Yes, its value is false. All right. Good. So the way that this typically comes up is something like this. So the most common situation that we'll find ourselves in is this one. So this is the definition of an equation in one variable. So, it's exactly, so this is exactly what it sounds like. So I'll just do it by example rather than trying to make a legal definition here. Is exactly what it sounds like. So some examples I could write. How about 13 x squared plus 1 is x. So in the first place, is this an equation? Yes. It has a left-hand expression, a right-hand expression, and an equal in between. Then, it's got numbers, real numbers, mixed in there, but it also has these variables, the letters, right? So notice that the left-hand side, how many letters are on the left-hand side? How many different kinds of letters? Just one, right? X's. And then how many different kinds of letters are on the right-hand side? Just one, X's. So altogether, how many different kinds of letters are there? Just one. So this is an equation in one variable. So is it an equation? Yes. Is there one variable? Yes. All right. Then we could do this one. So how about 4 w squared minus w is equal to 8 plus 10w. How about this one? So is it an equation in one variable? Yes. Right. It's not significant that variable happens to be named w instead of x. That's not significant. The only thing that is significant is there's just one of them. How about this one? 5a squared minus b is equal to 4a plus 7. So is this an equation? Yes. Is it an equation in one variable? It is not. Okay, so this is not the kind of thing that we're talking about. Would you care to speculate what we're going to call this one? An equation in two variables. Because mathematicians, we're notoriously naming stuff like that. Right. Okay, fine. What about this one? How about 13? I don't know. 13z squared plus 4z minus 8. Is that an equation in one variable? I only see one variable. Yeah, it's not an equation, right? So there's one variable, but it's not an equation. All right. Good. So here's how this kind of thing comes up. So consider 13x minus 8 is 14. So I'll just ask, but not bother writing it down. Is this an equation in one variable? Yes. Fine. So now, I forgot to say something. So, all right, so this, I'm going to say that this is blah. So right here I need to say a remark. Here's the remark, is that given an equation in one variable, notice, for example, this one that I crossed out. It's an equation in one variable, but currently, as written, it is not false or true or undefined. Its value is not determined. So it only has a value once you plug an x in. So right now, just looking at it, it's not false or true or undefined. It's not anything. So you've got to plug in an x to see, if it's going to be false or true or what have you. So given an equation in one variable, you can plug in values. Okay. So if the resulting equation is true, then that plugged in value is called a solution. Okay, otherwise, that plugged-in value is not a solution. All right, so now, that thing I was going to say. Okay, so now consider 13x minus 8 is 14. So now here's the first question. So 1. Is x equal to 2 a solution? Okay. So again, right now, we're not allowed to do anything on both sides. So like even the phrase solve for x, take this equation and solve for x, that doesn't mean anything right now. So right now all that we have is these definitions, and the question just is x equal to 2 a solution? So the only way to address it is just to say, well, I'll take that equation, and then everywhere I see x, I'll put 2. So 13 multiply 2, subtract 8 equal 14. So that's an equation. And then now I'll evaluate. So this would be 26 minus 8 equal 14. And so 18 equal 14. Well, what's the value of this equation? False. So what is the answer to the question? Is x equal to 2 a solution? The answer is no. It is not. Okay. Then I could ask, well, is x equal to 22 over 13 a solution? Okay, so it's the same question as before, just the number is different. So other than that difference, it's what you do is exactly the same. So we'll say, all right, this is 13 multiplied by 22 over 13, because I plugged that in for x, and then subtract 8 equal 14. So that's the plugged in thing there. So now the 13s cancel, so that you get 22 subtract 8 is 14. And then what is 22 subtract 8? Well, it's 14. So this now reads 14 equal 14. And what is the value of this equation? True. So what's the answer to the question? The answer is yes. It is. Now the point being is that a big part of this class is we're going to take equations, and the request in the end is going to be find all of the solutions. And you basically want to be able to given some equation, you want to be able to rapidly figure out that that 22 over 13 is a solution, and moreover, it's the only one. But before we do that, you've got to understand what it means to be a solution. So 2 is not a solution because when you plug it in, the resulting equation is false. And 22 over 13 is a solution because when you plug it in, the resulting equation is true. And we can't demonstrate it yet, but we'll eventually be able to say that, and moreover, 22 over 13 is the only solution to this equation. There aren't any others. Now, concerning equations, we'll be able to arrange matters so that we can have any number of solutions. So we can make it to where you could say, well, can you give me an equation that has no solution? Yeah, I can do that. So here's an example, just to make a simple one. So I could say consider. Just something very easy, like w plus 1 is equal to w. Now, you're not allowed to do the same thing on both sides. That's not permitted. Now, I know that you know about that, but that's illegal currently. So then I could ask, is w equal to 3 a solution? Well, we just need to take that equation, and then we just need to rotate the w's sideways so that they become 3's, right? So that it'll look like this. And then evaluate this and get 4 equal to 3. Of course, that is false. So the answer to this question is no. And do observe that, in fact, there isn't a w for which this will be true. Now, if we were allowed to operate on both sides and subtract w from both sides, the resulting equation would read 1 equal 0, right? And there isn't a w that can make 1 equal to 0. There isn't one. Okay. Now, if I just took this equation and just wrote that, just w equal to w, then would 10 be a solution? Yeah? What about 10 million? Yeah. In fact, every w would be a solution. So that would be an equation where everything is a solution. So we can arrange for there to be any solutions, any number of solutions in any locations that you wish. There can be 8 solutions. There can be 8 million solutions. There can be infinitely many solutions. There can be infinitely many solutions right there, but none over there. We can do it however you want. And the goal is going to be to find all those solutions. Okay, so to be able to do that, we need some rules about what is allowed. So let A, B, and C be in the reals. So you can think of this in the game of chess, there's different pieces, and they're only allowed to move in these ways. So like the queen can only move in her way, and the knights only in their way. So one of the legal moves is that given an equation, you can add the same number to both sides. But understand that because c is any real number, c could be negative, so this also means you can subtract the same thing from both sides. So that the resulting left-hand side would be a plus c, and the resulting right-hand side would be b plus c. Now, there's a subtlety to this that is easily overlooked. So here's what I want you to understand about this, is that if we start with a true equation, say 3 is equal to 3, it's true. And then if we add 2 to both sides, so the same thing, not add 2 there and add 4 there. No, do the same thing to both sides, like you've got a balance. Same thing to both sides. The resulting left-hand side is 5, and the resulting right-hand side is 5, and that's also true. So what I want you to see is that we started with a true equation, we added the same number to both sides, and the result is a true equation. So true to true. But understand that it works the other way also. If we start with a false equation, and we add the same number to both sides, the new left-hand side in this case would be 5, and the new right-hand side 9, and this is false. So false to false. So this is a legal move, because if it was true in the beginning, it's still true, and if it was false in the beginning, it is still false. Now, here's the place where students get messed up. The first place. There's several places, but here's the first one. So besides wanting to add or subtract the same number from both sides, another common need is to multiply or divide both sides by the same thing, so that the result would be A multiply C is B multiply C. So now, I'm going to leave myself a blank here, because this rule is not complete as stated. So here's what I mean. If we start with a true equation and multiply both sides by 2, then the result is a true equation. So, no surprises. If we start with a false equation and multiply both sides by 2, or even negative 2 maybe. Let's multiply by negative 2. So that's false. And then you multiply by negative 2, so you have negative 6 is negative 14. Of course, that's false. So far, so good. But here's the place where it breaks, is that I can start with a false equation, So this is false. And I'm gonna multiply both sides by a number, and the result is going to be true. And as a result, that's going to be an illegal move. That's not something that's permitted. So what can I multiply both sides of the equation by so that the result will be true? 0, right? It has to be the same thing on both sides. So if you multiply both sides by 0, then what's the new left-hand side? 0, and the new right? 0. So do you observe that that's true? So, you know, add, subtract, multiply, and what's the undo for multiply? Divide. So this is saying that multiplication of an equation both sides by 0 is not permitted. This is permitted as long as C is not 0. If C is 0, then you're breaking stuff. This is just another way to see that it's not allowed for you to divide by 0. Because if you could divide by 0, then you should be able to multiply both sides of an equation by 0 and preserve the truth. But that clearly does not work. Okay, so that's all that we have for today. I hope you have a wonderful Wednesday.